the concluding part of motion in 2 dimensions. So I am here again to share what we call projectile motion. Now, about projectile motion, we might have studied in our early classes that it is thus the motion of a body. You can write the motion of a body after projection. So the motion of a body after projection, that is when you have actually impart some initial velocity, impact of initial velocity into it. Initial velocity is termed as projectile motion. Now, for projectile motion, there are different types of projectile motion we can actually explain, but I will only limit my explanation to what is required in the syllabus of JUPEB, JAM, or UTMA, whatever you call it, and as well as a WAEC student. So about this, I will only talk about what we call the projectile of a motion of a horizontal ground. So let us discuss about projectile under gravity and explain the analysis of gravity potential. So let's discuss about projectile of a body, projectile under gravity. I think that would be the best way to put this for analysis and methodology that are involved in understanding projectile. So to actually analyze that very well, let us look at this diagram and bring this diagram to all our explanation as discussed in the initial phase of our projecting. Now, as you can see, we have our XY plane, which is an example of 2D type of motion already discussed, and we are talking about body that was what? That was in impact with initial velocity. This is the body. Let's take the initial angle of projection to be theta. Then what we have understand from early classes is that there is a ground, body was projected, was impacted with initial velocity u initially, then it will follow this path. Place diagram not drawn to say, and it will land at the same angle. The body at this component will be retarded by gravity, we call g. Remember, this is the x component, this is the y component, already discussed under introduction to 2D motion. Now, from the analysis of what we have understand, the body was projected at an angle of theta, follow a trajectory path. These are the paths, the motion of a projectile motion. In early classes, you have been told that this is what trajectory, very, very important for objective-based question. Now, when we talk about trajectory or the motion part of our projectile motion, or if you like, you can say parabolic in nature. Now, we say at this point, which is the x direction, we can say the velocity of the body along the x plane, already discussed, is ux cos theta, because the body here is going in that format, and here it is being retarded by d. We say at the y component, we write uy can be u sine theta. All this has been discussed under the introduction to motion in 2 dimensions. Now, having said that, the body is starting at initial time. We try to treat this, which is t, and reaches a particular height. We can see at this point, it follows this path, the same point to go and landed here. So when the body is moving on the horizontal direction, we said the body is not accelerating. We take acceleration to be 0. So please, students should keep that in mind. And when body is moving in the y component, as you can see, the body is being retarded by g. We say a is equals to negative g. Everybody should know that. So now, we cannot talk about projectile-based question on gravity or on horizontal ground as discussed without talking about some parameters and methodologies and formulas we use to solve questions. So some of the formulas are what we are going to be deriving here, and let's talk about them. And a very quick one because of time. Actually, it's 20 minutes for concept, and other time is for calculation. Now, standard parameters we talk about, and the derivation might be important for JUPEB students. Standard parameters, we talk about the first thing which is important is talking about what we call the time to reach the maximum level. Now, let us quickly analyze this in a quick way. As we can see that the body was going with initial velocity u, angle of theta, it moves up and reaches a particular height, which we can see here. So if I take this particular point that the body starts from t equals to 0, this here, and we reach this particular point, you can see when the body is going up, it reaches the maximum height. You can call that H maximum, which is very simple to understand. This is the maximum height the trajectory can actually reach. Now from here, we can quickly analyze something here. When a body is thrown up, reaches this height, at this particular point, the final velocity we call V at that point is equals to 0. You can see it's at y-axis. So I take the what? When a body, we have already discussed this under motion in one dimension, that is linear or rectilinear motion. So here, the first parameter I'll talk about is a body was thrown off from time t here to a what? T equals to 0 to a particular point here at time t equals to t, which we don't know. So the standard way of analyzing this, and we can say the time it will take this body to reach the maximum height, which is the first time, which is the first parameter we derive, is what we call the time to reach, a quick one guys, the maximum height. So we can take that here from our equation of motion in one dimension already discussed. We say, because the body is going in the direction of up, so we can say V is equals to U minus GT. I hope students still remember this linear equation. Now the body is moving in y vertical plane, so we can say V is equals to U here in this case is U sine theta, as you can see, U sine theta minus GT. So you can see this now, we have minus GT, that is G, which is the gravity, times T. So from here we can quickly analyze and say that the final velocity of the body is 0. So you can conclude here, my dear student, and say is 0, which is here, is equals to U sine theta minus GT. So from here, we can make this sort of formula, which is the time to reach the maximum height, and say time t is equals to, we have a U sine theta divided by G. So this is the way we actualize, and this is the way we relate the time it takes a body undergoing a parabolic motion or projectile motion to reach the maximum height. Now again, if the body reaches here, I have discussed that before, we can also calculate the time it will take the body to reach or to come back to where it's starting from. It will not stay up, it will come down. So we say it will take what? The time for the body to come back to where it is starting from will be what we call the time of flight. So that is another standard parameter you can always keep in mind, and that is denoted by capital letter T. The same time it takes to reach up will be the same time the body will take to come down. So in this case, we say U sine theta over G plus U sine theta over G. You have 2U sine theta over G. So these are the first two parameters which students need to keep in mind for direct based questions that involve substitution when angles of projectile are given initial velocity and stuff like that. All this might have been studied in early classes. The next parameter I'll quickly talk about, I'm talking about the fourth parameter, is what we call the maximum height. Now, the maximum height, if we look at this very well, it is very simple to understand that the maximum height of a projectile, the body is starting from here, moves to this point. So we can use our equation of linear motion that we have studied, H equals to UT minus half GT squared. But for direct derivation of formula, I think it is better for us to use the simple one. I'm talking about maximum height, my dear student. Maximum height is the next factor, which we might also study. Now, from our equation of V squared is equals to U squared minus 2GH, we can conclude from here the body reaches, you can see 0 is here, so we can say 0 squares are 0 is equals to U squared minus 2GH. Remember, U is what? At this plane here is sine theta. So therefore, I can just write is 0 is equals to U square will now be, you can see this U sine theta all square minus 2GH. I hope students are getting this. So if we make maximum height the subject formula, which is 8, I will turn it to capital letter, never mind. It will now be U square sine square theta over 2G. I believe this is direct, and this is better for us to understand all this. So you can also keep this in mind, and this is what we call the maximum height attained when a body is projected under gravity. So we have the two formulas. We have three so far, so good. The first, the second, the third. Now let's talk about the last one. When the body is going or it's moving along the what? The ground, which is the x-axis, and the direction here along this point is called the range. Now let us quickly analyze the range of a projectile motion. Doing so, we are going to move this up a little bit for understanding of the last concept. Now about this, we can say the next standard parameter we are going to discuss, like I said, is range. If you like to say horizontal range. The range of a projectile motion can also be deduced by using what our linear equation that we have discussed in early classes. Since we said the body is moving along the horizontal ground. So we can just say the range of a projectile, which is always towards the x-axis, can be said that the horizontal distance, which we call range is also called horizontal distance. For some of us who are beginners, or maybe in early classes, you don't actually understand what your teacher was actually saying. Now, the range of what? The range of a projectile motion we call horizontal distance is just the horizontal distance, or the speed or the time it takes the body to move from this point. You can see my lighter to this point because the body is moving in a parabolic manner. So the speed the body is taking from here to here, remember the body is not accelerating, so we can just say, and the time it will take the body to reach the maximum height. So we can say the product of the speed, remember S equals to ut, and the time, which is the time of flight it takes the body to reach the maximum height. You can see the parabolic movement I'm doing here. So it is just the speed, S equals to ut, and the time. Remember, u here along the horizontal is u cos theta. So r will now be equals to u cos theta multiplied by the time t. Time t, small letter t, I use it at time to reach the maximum height. So going by that, I'll say range here is now equals to, remember this guys, we have a u cos theta multiplied by, already discovered or derived, t here is a u sine theta divided by g. So everybody knows, oh, multiply by, the body has actually, sorry about that, should be capital letter T and not small letter t, because the body is going up and coming down. Look at it. This is the body speed. Then the body has gone up and also come down. So this should be 2u sine theta. This is the formula over g. So now we can say, therefore, from there, we can say, since from your trigonometry, you know that 2u sine theta cos theta is the same thing as sine 2 theta. Let me just help you write that. Since 2 sine theta cos theta from your trig ratio, and if you don't know, there's a first time to everything, is equals to sine 2 theta. So you can conclude that here, see, 2 sine theta cos theta is now changing to sine 2 theta. So what I have now will now be range equals to, you can see here we have u times u, that is u squared, sine 2 theta divided by g. So this is the formula we use to calculate the range of a projectile when we are talking about projectile motion on what? On horizontal ground. So always keep it in mind when you are solving questions that deals with all these, and the direct formula can be applied and can be directly used to get answers without wasting time. So now, another thing we need to talk about here before I finish this, and we continue in the next slide, in the next class, is to also discuss about what we call the maximum range, because it's very, very important to understand the concept of maximum range. And about the concept of maximum range, we can quickly analyze that here. Now, if you watch from our relationship that we have set here, it can be inferred or conclude that the range of projectile depends on angle. You can see the angle now. So we can say range of projectile depends on the angle of projection. So I can just write that for writing's sake, range of projectile depends on angle of projection. So from here we can say, now the body will actually depends on the angle. And if you look at this now, sine, from your trigonometry again, sine theta is always maximum. Sine theta is always maximum at 90 degrees. So, and if you watch here, what we can do here is just relate the angle in which it is depending on. It's depending on the angle of 2 theta. So if we go by that, we can say 2 theta is equals to, I said maximum value of sine on your trigonometry graph is 90 degrees. So student can keep that in mind. So 2 theta here is 90 degrees. So here you can say theta is equals to 90 by 2. Everybody knows 90 divided by 2 is 45. So we say at an angle of 45 degrees, the range is maximum. So from that, we can say if theta is now 45, 2 45s are 90, sine 90s are 1. So the maximum value of range for direct solution and application of formula will just be equals to u squared all over g. So this is the way we relate, and this is the formula we use to calculate range maximum, and this is what we are going to be discussing about in this slide. In the next slide, I'll talk about general equation of trajectory because of our JUPEP students to understand, and the type of a projection that is thrown horizontally and not in vertical direction. So see you guys soon, and please, you can always note, I think you need to note this as well, that the value of range at any point of projection can always be more than 1, because we said at an angle of 45, you can watch this, you can say, what am I saying? Yes, I know what I'm saying. Now here, angle of 45, we said range value with the maximum. That is what we are talking about. Now, if we try to project another body now, and it's moving like this, as you can see. Now, if the body is being projected at an angle that is not up to that, sorry about that diagram, let me make it, let's say around 52 degrees here. Now, we can also say that what, if we project another body at an angle that is complementary, what do I mean by complementary? That is, we said, the sum of angles that are complementary in our trigonometry is that angle you can add it together to, or you can add together to give 90 degrees. So if this was projected at an angle of 52 degrees, now I have another one that was now projected at an angle, let's say 48 degrees or 38, should be complementary like that. Dates now. So we can always have two positions of angle that will always be the same, because we know that in this case, theta 1 plus theta 2 is equals to 90 degrees. So if I have an angle of 52 and an angle of 38, if I add it together, the two will give me 90 degrees. So what am I trying to say from my mathematical relationship here? I am saying it is very, very possible for me to have different angles for what? Before what we can actually achieve at what a maximum range. There are possible, or there are two possible angles at which the range of a value of a projectile can be what? Can be maximum. And that is because the two angles that we are talking about must be what? Complementary angles, which basically we can say can be had together to give us 90 degrees. I believe you understand, and if you don't understand, layman way, what I'm saying is that maximum range occur at a particular angle of 90. So if we project two bodies at different angles, in as much the two angles are going to give you 90, so the body can what? Exhibit what? Maximum value of it. So this is where I will stop. So see you guys soon in the next slide. Thank you, and do have